Hello, everyone. Welcome to our presentation on Robocar, our real-time embedded system project developed as a part of the real-time software engineering course. In this video, we'll walk you through of how we designed, implemented, and tested line-following robot can detect the line-following robot that can detect obstacles, respond to environmental triggers, and navigate autonomously, all powered by real-time operating system. Our Robocar was built on the Arduino Uno platform using the 80 mega 328P microcontroller and used the UCOS 2 RTOS to manage real-time task scheduling. The robot uses multiple sensors, including line sensors, a proximity sensor, and a light sensor to interact with its environment, while actuators like DC motors, LED, and buzzer carry out the robot's actions. To achieve the real-time responsiveness, we designed and prioritized tasks such as collision detection, motor control, navigation, and LED blinking, each running with carefully selected time intervals. For instance, the collision check run every 20 milliseconds to avoid obstacles promptly, while navigation decisions are updated every 20 milliseconds for smooth line following. Through this video, you will see how we applied the concurrent programming, how task priority impacted the Robocar performance. So let's get
Startup.
started.
So today I will be talking about our first lab session. We had our first lab session on 18th of June. So in our first lab session, we basically started with the setup of everything. Yeah, we did download the software and other development tools earlier, but understanding simply how to get the code from our machines into the Robocore was one of the things that we learned at that day. Also, we try to put the code on the car, and as you can see in the video, here is what's going to be happening. The car moves, and the soon it moves, it detects a white color, and then it starts to reverse without going back forward. That's the one of the first trials we had. It was a completely foolish one, a completely failure, but we learned from that how to read the code as well. So we tried to read the code, read what instructions does it make it do this, which is the line sensor, and basically it was more about the line sensor. And then moving forward, we try to provide better instruction to it, and eventually we're able to make it go through at least some of the checkpoints.
So the second iteration of the code, the robot starts, it locks onto the central line using a line following logic that I adjusted. I only changed the sensitivity from the first logic, and then from the A to B section, the line is surrounded by large black boxes, so I turned the robot to follow the white path directly so it ignores the white black areas and doesn't get distracted by sudden changes in contrast. From B to C, it is in the tens. It is a little slow. I adjusted the logic so that it goes back every time to actually adjust its pathing, and then it for the obstacle detection, since once it detects the obstacle, it goes back and then it moves to the right side to make it all the way to the third point. And then here it actually just follows the black lines. It doesn't follow the dots in the middle, all the way up until E. It's pretty straightforward. And then it does the same thing again where it will turn very, very slowly up until it goes onto the black line for the square, and then it will just proceed accordingly throughout the entire track. So the adjustments, the robot encounters the checkpoint at B. I made sure the line following logic prioritized moving straight through when the sensor detects the line, uh, letting the robot pass checkpoints confidently without unnecessary turns. From C to D, the path has another vertical line. I optimized the sensor pattern handling so the robot treats this as part of the main path and continues forward if it finds a checkpoint. For the obstacle detection, I improved the obstacle detection by making it check the sensor much more frequently. So now the robot reverses and turns before, as soon as it detects the obstacle. It honks and it does a sharp right turn. So that it can avoid the obstacle and then proceed with the track. And then for the light detection at the start of the video, as soon as it detects the light, it will do the LED lights throughout the entire track. As you can see, it did honk once and now it's flashing the LED light until the end of the track. So that's the logic changes for the second iteration of the code.
During game day, unfortunately, we couldn't manage to copy in the correct code into the car because we have changed the directory and accidentally changed the code. So we couldn't copy in the code that we have done already in session 2, which was already working. Unfortunately, our car didn't make it past the point A. It only went from point 0 to A, and then A to B started to failing, and then the referee called for times up, and we unfortunately couldn't manage to make it to the end of the race. But overall, the experience was very good. It was our first time trying to program a real-time robot that during our first 4 years of studying computer science, we have never had any experience like that, experiencing real-time concurrency and how to program and try to tune the numbers and try to fit in the tasks, scheduling it in a perfect way that it can handle these obstacles and follow the wanted commands and lines. All right, and this was a wrap for our assignment 2, the robot car programming, and I hope you guys enjoyed the video. See you next time.